Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of today's lecture is Temperature Distribution for a Fully Developed Flow of Newtonian Fluids in Tubes. So, the major constraint of this problem is the flow is fully developed. So, whatever the temperature profile that we are going to obtain for the case of Newtonian fluids flowing in tube under non-isothermal conditions, this temperature profile is applied only for that region of the tube where the flow is fully developed. Actually, this problem we have taken previously under isothermal conditions. So, where we tried to obtain the velocity profiles for the power law fluids, right, and then we substituted n is equals to 1 and then got the velocity profile. So, that we know actually. So, that we have to revisit here. Actually, since we are finding out the temperature profile and then energy equation, there is a velocity term. So, then we must know the velocity profile as well for that given profile, for that given geometry. Okay. So, for fully developed flow conditions, especially for circular tubes, what we have taken L by D is very large, in general more than 150 or something like that, or 100 to 150 something like that we have taken, right. That also depends on the nature of the fluid. Sometimes even 100 L by D of 100 is sufficient, sometimes even L by D of 200 may also not be sufficient if it is a viscoelastic fluids. So, that is a different issue, right. So, what we see under such conditions, the flow is fully developed. We take only that region of the pipe in which the flow is fully developed. Fully developed in the sense, in the flow direction, dou, let us say in the z direction flow is taking place, dou by dou z of any velocity or vector components etc. are going to be 0. That is what we have seen, right. So, now the same we are revisiting again the same problem, but only thing that now we are taking non-isothermal conditions, right, and then that non-isothermal conditions are also such a way that the delta T or temperature difference whatever is there, it is not affecting the Cp, rho, mu etc. this kind of physical properties. These things are not being affected by the temperature, right. So, that means velocity profile is not function of temperature, but the temperature is function of velocity as well, right. So, that is the reason for this case we have to find out the velocity profile and then that velocity profile we have to incorporate in solving the energy equation. Okay. So, now here the coordinate system stand the same problem. In the flow direction we are taking z, other direction we are taking r, right. If it is fully developed flow, when we simplify the momentum equations etc., what we understand, tau rz is equals to minus delta p by L, r by 2, that is what we obtain. So, that means the shear stress is linear. So, that is what shown here. And then velocity profile we have seen, like it depends on the power value of n, because we have done it for power law fluids and then Bingham plastic fluids separately. Individually for Newtonian fluids we have not done. So, but that velocity profile, if you substitute n is equals to 1, you get the parabolic velocity profile that is given here, right. So, now we are bringing in this non-isothermality in this problem, so that to find out the temperature profile also, but only for the fully developed region of the geometry, not for the entire entry to exit, because when we are saying the fully developed flow, end effects, that is entry effect and then exit effects are negligible, right. So, whatever the solution, whether the velocity distribution that we already got or the temperature distribution that we are going to get today, it is not valid region close to the entry, region close to the exit, in between only it is valid, and then especially L by D has to be very large. Okay. So, now we give the conditions, like what are the velocity conditions, boundary conditions are required. So, at wall no slip condition, so velocity is 0, we know. At center velocity is maximum, so Vz is equals to Vz max, that we know. That is sufficient for in order to get the velocity profile, this parabolic profile that we can get, that is Vz is equals to Vz max multiplied by 1 minus small r square by capital R square, that we can get using these boundary conditions. But temperature profile you have to wanted to find out, you have to have the conditions with respect to the temperature also. So, let us say at the inlet the temperature is T1, and then this wall, whatever the pipe walls are there, they are maintained at constant heat flux Q naught, right. And the temperature at the center, what it is we do not know, whether it is maximum or minimum or whatever, we do not know. So, what we are saying that temperature is finite at the center, T is finite at the center, that is at R is equals to 0, it is finite, that is what we are saying. Fine. So, now three conditions are there for temperature. So, we have to find out. Another thing that most important thing, for the velocity profile in this fully developed region, we found that it is function of R only, right, and then accordingly we got the velocity distribution, and then that is true also if we have one dimensional laminar flow. So, definitely it stands well, but under such conditions, even though velocity is function of R only, you cannot say the temperature is function of R only, it may also be function of Z, especially because the temperature condition at the inlet is different from the wall conditions, center temperature conditions. So, now here more than one variable is coming into the picture. So, whose effect should also be taken into the consideration. So, now even though here in this problem the velocity is function of only R, but temperature is function of both R and Z. So, now the problem becomes more complicated to solve mathematically. So, however, there are certain approaches, certain certain types of solutions are available, approximate solutions which are almost close to the reality. So, those things we are one of such kind of solution we are going to discuss now. So, what we have to do here, first we have to list out the constraints of the problem, then solve the simplify the momentum equations, then get the velocity profile, then after that simplify the energy equation. In that energy equation, if the velocity terms are there, so then substitute the velocity distribution, then simplify the simplified energy equation to get the final temperature distribution. So, those are the steps. Okay. So, first constraints or assumptions of the problem. Newtonian fluid with constant physical properties, rho, mu, etc. are not changing even though non-isothermal conditions are there. Then steady laminar incompressible non-isothermal flow. Previously what we have taken, when we are taking only momentum transfer, we have taken isothermal flow, but it is non-isothermal flow in this case. So, temperature profile one has to find out. Flow is fully developed, no gravity, no reaction, no viscous dissipation, no reaction kind of things, standard, and then only Z component of velocity is existing, that is function of R, whereas V theta, Vr are 0. But temperature is function of both R and Z, that is T is function of both R and Z. Then boundary conditions for the temperature we are writing, because for the fluid we already know very simple ones. At the center at R is equals to 0, we do not know whether it is maximum, minimum or negative, positive, we do not know anything, right. So, then what we are saying that it is a finite value, just finite, and then walls are maintained at constant heat flux. Okay. At the inlet, that is Z is equals to 0, T is equals to T1. Since T is function of Z also, we need to have a boundary condition as function of Z also for different values of Z also. So, for the time being it is given only at the inlet, that is at Z is equals to 0 only the temperature condition is given, that is T is equals to T1, right. Now, we solve the problem. First we write the continuity equation in cylindrical coordinates, then we have this one steady state. So, this term is 0, Vr is not existing, V theta is not existing, and then fully developed flow. So, dou by dou Z of anything is 0. So, continuity is satisfied. R component of equation of motion is given here, Vr is not existing, and then steady state term. So, it is 0, Vr is not existing, V theta is not existing, Vz is there, but Vr is not there, V theta is not there, pressure in general we do not know, Vr is not existing. So, all these three terms are not there, V theta is also not existing, the gravity we are not taking, horizontal pipes we are taking. So, pressure is not function of R. Then theta component of equation of motion is given here. So, steady state this term is 0, Vr is not there, V theta is not there, Vz is there, but V theta is not there, Vr, V theta both are not there. So, left hand side all terms are cancelled out. The pressure dou p by dou theta 1 by the pressure term we do not know in general. So, we just keep it as it is. V theta is not there, so this term is 0, this term is also 0, this is also 0, Vr is not there, so this is also 0, gravity we are not taking. So, what we understand, pressure is not function of theta. So, pressure should be function of z only, because in the z direction flow is taking place, and in that flow is taking place because of the pressure gradient. It is the same problem we are revisiting for a Newtonian case. This is exactly the same problem we have done for the power line and Bingham plastic fluids previously. So, z component of equation of motion is given here. So, steady state this is 0, Vr is not there, V theta is not there, Vz is not function of z, or fully developed flow, this is 0. The pressure in general dou p by dou z now we do not know. So, let us keep it as it is. Vz is there and it is function of and it is function of r. So, this term would be there. Vz is not function of theta and z. So, these two terms are 0, there is no gravity. So, dou p by dou z is equals to mu by r, dou by dou r of r, dou Vz by dou r, this is what we are getting. So, this equation if you solve, then you get Vz as function of r. But now already we understand that pressure is not function of r and theta. So, when we integrate this equation, left hand side is only z pressure and then z terms are there. So, velocity is not function of z. So, when you integrate this one, you can take the left hand side term as a constant when you integrate the right hand side term. Similarly, right hand side only function of r is there, okay, but pressure is not function of r. So, when you integrate the left hand side term, what you can do? You can take a right hand side as a constant and then integrate it. Okay. Since pressure is not function of r and theta, but it is function of z only, and then dou p by dou z whatever is there, that you can treat it as a constant, and then when you integrate, you get the pressure P is equals to C1z plus C naught. At z is equals to 0, P is equals to P naught. So, C naught is equals to P naught. At z is equals to L, P is equals to PL. So, that means PL is equals to C1L plus C naught, and then C naught is nothing but P naught. So, that means C1 is equals to PL minus P naught by L. That means P is equals to minus delta P by L Z plus P naught, that is what we can write, or dou P by dou Z is equals to constant C1, and then that C1 is minus delta P by L. So, now this equation in place of dou P by dou Z, this is the equation that when we simplified the Z component of equation of motion, this is what we get in the previous slide, one of the previous slide. Now, dou P by dou Z in the previous slide we got it as a constant, that constant is minus delta P by L. So, minus delta P by L is equals to mu by r, dou by dou r of r dou Vz by dou r. So, that we can write minus delta P by L r by mu is equals to dou by dou r of r dou Vz by dou r, and then when you integrate minus delta P by L r square by 2 mu plus C1 is equals to r dou Vz by dou r. This r you take to the left hand side. So, minus delta P by L r by 2 mu plus C1 by r is equals to dou Vz by dou r, and then once again if you integrate, Vz is equals to minus delta P by L r square by 4 mu plus C1 ln r plus C2. Now, when you apply the boundary condition at r is equals to 0, Vz has to be maximum, but ln of 0 you cannot define. So, then this C1 constant has to be 0, and then at r is equals to capital R, Vz is equals to 0, then C2 you will be getting minus of minus delta P by L capital R square by 4 mu, and then this C2 you substitute here, C1 is 0 anyway, then minus delta P by L R square by 4 mu, if you take common you get 1 minus small r square by capital R square, that is the velocity profile that we have the parabolic nature for Newtonian fluid, right. This minus delta P by L r square by 4 mu you can write it as Vz max, because in this equation if you substitute r is equals to 0, it will be Vz max, because at r is equals to 0, that is at the center of the pipe velocity is maximum. So, at r is equals to 0, Vz is equals to Vz max. So, in this equation, if you substitute r is equals to 0, you will be having only minus delta p by L r square by 4 mu, that I am writing Vz max. So, this is what we have. Now, equation of energy we are going to simplify. Okay. In cylindrical coordinates, equation of energy is given here. Steady state, this term is 0, Vr is 0, V theta is 0, Vz is not 0, and then temperature is also function of z in addition to function of r. So, this term should be there. Temperature is function of r, so this term would be there, but it is not function of theta. So, this term is cancelled out, this term is there because temperature is function of z. What function it is, we do not know, that we are going to obtain now, right, and then we are not taking any viscous dissipation in this problem. So, what we have, rho Cp Vz dou T by dou Z is equals to K multiplied by 1 by r dou by dou r of r dou T by dou r plus dou square T by dou Z square. Now, can we further simplify this equation? That is what we see. So, this term indicates the conduction in the radial direction, this term indicates the conduction in the z direction, this term indicates the convection in the z direction. So, flow is taking place in the z direction. So, in that direction convection is going to be dominating compared to the conduction. So, what we can do? We can cancel out this term dou square T by dou Z square with that comparison to rho Cp Vz dou T by dou Z, or otherwise also if you take only conduction terms, conduction is going to be dominating in the direction normal to the flow, that is in the r direction. So, in compared to, so conduction is going to be more in the r direction than in the z direction. So, by that analysis as well, dou square T by dou Z square we can cancel out. So, by either of the reason, when you cancel out dou square T by dou Z square, you will be having rho Cp Vz dou T by dou Z is equals to K by r dou by dou r of r dou T by dou r. So, now here in place of Vz, what we write? We write Vz is equals to Vz max 1 minus small r square by capital R square. So, then this is what we are having. This equation we have to solve. So, obviously from this equation what we understand, we need two boundary condition for r with respect to the r, and then we need one boundary condition with respect to z, right. So, boundary condition what we have, at the center temperature is finite, we do not know how much it is, we are saying finite. Okay. Obviously, it cannot be 0, it can be maximum or cannot be maximum, that also we cannot say. So, but we are saying finite. Okay. And then at wall we are maintaining the constant heat flux, that is Q naught is equals to K dou T by dou r, right. And then at Z is equals to 0 at the inlet, we know the fixed temperature T is equals to T1, constant inlet temperature, right. So, now equation 1 using the boundary conditions given in equations 2, 3 and 4 we have to solve. So, equation number 1, now what we do, rather solving in this form we make it non-dimensionalized, right. So, now here scaling parameters are given here. So, capital theta is nothing but dimensionless temperature, right. In the previous problem you may be thinking that delta T is non-dimensionalized using the T1 minus T lambda or T lambda minus T1 whatever, but now here why are we taking Q naught r by K to non-dimensionalize the temperature difference? Because we know only one fixed temperature, only T is equals to T1 at Z is equals to 0, that much only we know. We need at least two temperatures if you wanted to non-dimensionalize the temperature difference using the temperature quantities. So, that is not possible here because we know only one temperature quantity T1. So, that is not possible. So, that is the reason Q naught we are using, that is constant heat flux, right. So, capital theta is the dimensionless temperature which is T minus T1 by Q naught r by K, and then dimensionless radial coordinate whatever is there, small r by capital R, we call it xi, right. Now, this z, dimensionless z coordinate also we have to define. How to define? Let us say this equation number 1 if I write 1 minus r square by capital R square dou t by dou z divided by 1 by rho Cp tilde Vz max, right, is equals to this k also I am bringing it here to the left hand side. So, k by rho Cp Vz max is equals to 1 by r dou by dou r of r dou t by dou r, right. So, now whatever these things being multiplied by this coord z, that we are taking as a kind of scaling parameter to non-dimensionalized z. So, dz whatever z things is there, that is multiplied by r square rho Cp Vz max by k from this equation. So, that is the reason dimensionless z, that is zeta is equals to z by rho Cp Vz max r square by k we are taking. Sometimes this comes with experience also. So, that is what we are doing here. Okay. So, otherwise you may be confusing, because non-dimensionalizing the radial coordinate, you are simply dividing that one with the radius of the tube. Okay. Temperature difference, you are simply taking the constant heat flux terms and then doing it. But in this case of z, it is not so simple, because there is no another L coordinate L kind of thing in this equation. Otherwise, z by L we could have taken as zeta, right. So, that is the reason we have written like this. How to select? Now you can that you have to rearrange like this way, and then whatever the terms being multiplied by this z terms whatever are there. So, that you take as a kind of a scaling parameter to non-dimensionalize the z coordinate, fine. So, now these scaling parameters we are going to use to non-dimensionalize this equation number 1. So, in the equation number 1 we are having dr, dz, dt terms are there. So, now from this capital theta what we can understand, dt is equals to q naught r by k dt, d theta, capital theta, right. From this xi definition, dr is nothing but capital R d xi, and then from this zeta information, dz is nothing but rho Cp tilde Vz max r square by k d zeta. So, now we apply these things in this equation number 1. So, what we will have rho Cp tilde Vz max multiplied by 1 minus r square by r square is nothing but xi square, delta t is nothing but q naught r by k d capital theta divided by dz is nothing but rho Cp tilde Vz max capital R square by k d zeta is equals to k, small r is nothing but zeta xi capital R, small r is nothing but xi multiplied by capital R, d by dr is nothing but capital R d xi of r is nothing but xi capital R, and then d theta is nothing but q naught r by k d capital theta divided by dr is nothing but r d xi. So, now this is the equation. So, this rho Cp tilde Vz max, this rho Cp tilde Vz max cancelled out, right. So, this q naught r by k and this q naught r by k is cancelled out, this r is cancelled out, right. So, now here r and r square is there. So, this r square is cancelled out, and then this k cancelled out. So, what you get from this equation, 1 minus xi square d capital theta by d zeta is equals to 1 by xi dou by d xi by d xi of xi d capital theta by d xi. This is what you get. So, this same equation, simplified final equation, is written as a equation number 5 here, right. So, now boundary conditions also we have to define in non-dimensionalized quantities, right. At r is equals to 0, t is equals to finite, that is the boundary condition. If r is equals to 0, that means xi is also 0, and then if t is finite, so theta, that is t minus t1 by q naught r by k is there. So, that should also be finite. We do not know how much it is, we just write it as. Then at r is equals to capital R, that means xi is equals to 1, and then what is the boundary condition? The constant heat flux, that is q naught is equals to k dou t by dou r, right. So, at r is equals to r, constant heat flux q naught is maintained, that is nothing but k dou t by dou r. Forget about the minus, plus and all that is not required. Okay. So, now q naught is equals to k, delta t is nothing but q naught r by k d capital theta, this entire divided by dr is nothing but capital R d xi. So, this q naught, this k, this r is cancelled out. So, d capital theta by d xi is equals to 1. So, that is what is this one. And then at z is equals to 0, theta is equals to, at z is equals to 0, t is equals to t1. If z is equals to 0, that means zeta is equals to 0, right. And then if t is equals to t1, so theta is going to be t1 minus t1 by q naught r by k. So, this is going to be 0 anyway. So, that is this one. Okay. So, now we are going to solve this equation number 5 using the boundary conditions given in equation 6, 7, 8. So, obviously, it is not possible without making certain kind of approximations, okay, because now temperature is function of r and z. So, theta is also function of zeta and xi here. Okay. So, what are the approximations we do in general that we see? We are taking asymptotic solution. First one is, it is possible for large values of z or zeta, because it has been mentioned that temperature profile for a fully developed flow region. So, that is true only for large values of z. Okay. Then after fluid is sufficiently far downstream from beginning of heated section, one expects that constant heat flux through wall will result in a rise of fluid temperature which is linear in z direction or zeta. So, let us say this is the pipe. Okay. So, now we are far away from the inlet and outlet. So, where the velocity profile is fully developed, right, and then we are having some parabolic profile like this. So, in this region what happens? So, whatever the variation in the velocity is not there. So, variation in the fully developed region only, variation in the velocity in the flow direction are 0, isn't it? So, that means the with respect to the wall, the fluid relative motion between wall and then fluid regions is going to be same. So, then obviously that velocity is not going to affect much the temperature profile here in the fully developed region, and then that also in which direction it will not affect? It will not affect much in the z direction. The convection whatever is there, that is not going to affect the the velocity profile is not going to affect the heat transfer because of the convection much. So, only whatever the variations are there in the z direction, they are expected to be linear. Okay. So, temperature profile whatever is there, T function of Z or T function of zeta is there, that is a linear, that is what we are saying, because velocity profile is not changing in the flow direction, that is in the Z direction. Then also expect that the shape of temperature profile as function of zeta will ultimately not undergo further change with increasing zeta or Z value. So, whatever the variation in the temperature profile is there, so T as function of R is there, so that is not affected by the temperature variations in the Z direction for the further longer increasing zeta values. So, basically what we are trying to say, what we are trying to do here now from these two assumptions, from these two assumptions we are saying that whatever the T function of R and Z is there, so that we are trying to write T is separate function of R and then T is separate function of Z, and then we are taking their effects as a additive, and then that is quite possible if the flow is fully developed. So, then we have this temperature non-dimensionless temperature would be having this form. This is the form of the solution now. This is not the problem equation, this is solution equation, right. So, what we understand from these two assumptions, the temperature is a linear function of zeta. So, C naught zeta, and then whatever the temperature as function of R or theta as function of xi is there, that is not affected by the temperature variations in the Z direction. So, in this this part it is only function of xi, it is not function of zeta, okay, that is what we are trying to do. So, now if you find out what is this C naught constant and then what is this psi function of xi whatever is there, that you find out, you got the solution, okay. And then this solution should also obey the boundary conditions that we have, 3 boundary conditions, equation 6, 7 and 8. Then only we can say that whatever the assumed form of the solution, this is assumed form of the solution, okay. So, then we can say that is approvable, or otherwise do we need to make any amendments, that we have to see. So, we will check equation first boundary condition is that at xi is equals to 0, theta is finite. So, if let us say this second term psi function of xi whatever is there, if it is having all the terms xi terms. So, if you substitute xi, so the second term is going to be 0, but despite of that one this term is going to have some value. So, then theta is equals to finite is possible even when xi is equals to 0. Then when xi is equals to 1, dou theta by dou xi is equals to 1, is it possible or not? When you do the dou theta by dou xi, you will get dou psi by dou xi, right. So, this is function of xi. So, then we substitute xi is equals to 1 here. So, then it is possible that you may get 1, right. So, it is possible that kind of psi function you can find out, right. So, now this second boundary condition is also satisfied. So, the solution 9 is satisfying boundary condition 6 and 7. Then boundary condition 8, is it satisfying or not, that we have to check. When zeta is equals to 0, then theta is equals to 0. So, let us say if zeta is equals to 0, then theta is 0. Yeah, that means this all that is possible when altogether this function is 0, but that is not possible. So, that means this boundary condition is not being satisfied by this form. So, then what we do? We have to obtain one conditions for the z direction also. So, that we try to do it. How we try to do? Let us say this is the pipe. So, at certain location z. So, from the inlet z is equals to 0 to certain location z is equals to z whatever is there. So, heat is coming in because of the constant heat flux. So, whatever the 2 pi r V z q naught is there. So, that should be balanced by the whatever the rho C p. Now, here rho C p t V z r dr d theta on integration whatever the quantity is there. So, that is at z is equals to z. The same quantity at z is equals to 0 is nothing but rho C p t 1, because at z is equals to 0 t is equals to t 1 V z r dr d theta. This also you integrate whatever the quantity is there. So, that is the rate of heat in at z is equals to 0. So, rate of heat out at z is equals to z minus rate of heat in at z is equals to 0, that should be balanced by the whatever the heat being supplied through the wall from z is equals to 0 to z is equals to L. So, that balance when you do, you get these things, that is 2 pi r z q naught is equals to integral 0 to 2 pi integral 0 to r rho Cp T minus T1 Vz r dr d theta. Now, the temperature is not function of theta. So, you can write 2 pi integral 0 to r rho Cp T minus T1 Vz r dr, that is it. Then 2 pi will be cancelled out. Now, here also you apply this same scaling parameter exactly, then you get this boundary condition. How, let us, you can check it is, let us say 2 pi r z left hand side is same, q naught is same, right hand side 2 pi integral r is equals to 0 means z is equals to 0, r is equals to capital R means z is equals to 1, then rho Cp T, what we are using T minus T1 is nothing but theta multiplied by q naught r by k multiplied by Vz, Vz we are writing Vz max 1 minus r square by r square is xi square, and then dr is nothing but capital R d xi, r is nothing but r xi. Okay. And then left hand side in place of this z, what we have to write? Zeta rho Cp Vz max r square by k in place of z. So, this 2 pi is cancelled out, this q naught is cancelled out. So, here 1 r and then another r here is cancelled out, this rho Cp here it is cancelled out, Vz max is cancelled out. So, this r square would be getting from here, only 1 r is there. So, then from this 1 r, then square of this r is gone. So, then this r is gone. So, then what we have, left hand side we have only zeta is equals to integral 0 to 1 theta, which is function of xi and zeta multiplied by 1 minus xi square, and then here xi d xi, this is what you get. You can simply do it, practice it, and then you can get this equation. So, this is the third boundary condition that we got. Now, the solution whatever is there after this part very mathematical. So, this is your solution, this is your governing equation. So, now this equation you can substitute here. So, this equation should be satisfied. So, let us say from this equation dou theta by dou zeta is nothing but C1. So, I can substitute here in place of this one is C1. So, 1 minus xi square C1 is equals to 1 by xi dou xi of xi dou psi by dou xi I get, because dou theta by dou xi is nothing but dou psi by dou xi, is not it? So, that when you do 1 minus xi square in place of this one is C1, in place of d theta by d xi I have to write dou d psi by d xi, right. So, this is what we are having. When you expand left hand side, this also you take to the left hand side. So, then you have xi minus xi cube C naught and then this one, right. So, next what you do, integrate it. So, xi square by 2 minus xi power 4 by 4 C naught plus C1. So, this psi you bring it to the right hand side again. So, then this is what you are having. Once again if you integrate, you get xi square by 4 minus xi power 4 by 16 C naught plus C1 ln xi plus C2. So, this is this psi function whatever is there. So, is this one. So, this unknown function you got it now by given equation number 13. So, now overall final solution we can have theta is equals to C1 zeta plus C naught xi square by 4 minus xi power 4 by 16 plus C1 ln xi plus C2. This is the final solution. Only thing that what is the C1, what is the C0, C1, C2 that you have to find out. So, that we can find out simply by using boundary conditions. So, this is the solution. First boundary condition is at xi is equals to 0, theta is equals to finite. That means, if you substitute 0 here, ln 0 is not possible, so C1 has to be 0. And then second boundary condition, at xi is equals to 1, dou theta by dou xi is equals to 1. So, from this equation, dou theta by dou xi is nothing but C naught xi by 2 minus xi cube by 4 plus C1 by xi. C1 is anyway 0 from boundary condition 1 after applying the boundary condition 1. Then xi, if you substitute 1 here, 1 by 2 minus 1 by 4 is 1 by 4. So, that means C naught is equals to 4. Then third boundary condition is this one, right. Zeta is equals to integral 0 to 1 theta 1 minus xi square xi d xi. So, xi minus xi cube d xi you can write. Theta you can substitute, theta is this one. So, all the terms are being multiplied by xi minus xi cube. Now, you looks like lengthier, but simple. You integrate this equation and then substitute C naught C1 and then get C2, then C2 you get minus 7 by 24. So, all the constants C naught C1 C2 you got it. So, then final solution you got it. So, that is theta is equals to in this form, that final solution C naught you substitute 4, C naught is 4, C1 is 0. So, then this term is anyway 0, then after substituting you get this final solution for the theta. Theta, capital theta as function of zeta and xi you got it, okay. But finally what you have, what you need to have? You need to have temperature in dimensional form. So, dimensional form T is equals to T1 plus Q naught R by K multiplied by theta. This is coming from your theta scaling parameter definition, that is T minus T1 by Q naught R by K. So, now here in this equation in place of theta you substitute equation number 15. So, then you have this final solution for the temperature distribution of a Newtonian fluid under fully developed flow conditions. Alright. So, this temperature distribution for a Newtonian fluid flowing through pipe, but the flow is under fully developed flow conditions. Temperature profile is also valid for only fully developed region, not valid for entry and then exit regions, valid for only fully developed flow region only. If you have to include the entry exit regions also, then you have to do using the numerical solution, otherwise it is not possible to get approximate solutions like this. This problem is taken from this reference book. Other useful references are provided here. Thank you.